This is the 9th video on differentiation, where we're going to have a look at second derivatives. So that's how we can differentiate for a second time, what that represents and how we can use it. Before we do that, I just want to take a step back and talk a little bit more about notation and the way we write things down. So I want to talk about the derivative operator, because it's something I've not really talked about in these videos so far, not explicitly anyway. We've seen dy by dx written down quite a lot. Now what we've been doing when we've worked out dy by dx is worked out the change in the y coordinate with respect to the x coordinate at a particular point. So in all of those things, if you take out the y for a minute, ignore the y coordinate for a minute, what we've been working out is the change in something with respect to the x coordinate. So this is your operator, this is what you're doing to something. In all of our cases so far, it's always been the y coordinate. So what we've been doing is working out the change in our case y, with respect to x. So this is your derivative operator, d by dx. So when we do it to y, then we get dy by dx. You'll see it in the next video. It doesn't have to be y, it can be any variable at all. But I want to bring this up now because it will help us, well, it'll help me hopefully show you how and why we write down the second derivative the way we do. So let's just go back and think, what's the first derivative mean? Well, when we say dy by dx, we're working out the rate of change of the y coordinate. The y coordinate is your quantity or the size of something, whether it's the size of the y coordinate or you'll remember from when I first introduced this topic, I was talking about the thoughts that Isaac Newton was having regarding gravity, and in that case it would be the size of the gravitational force. So when we have this function, it's just representing the quantity or the size of something. When we differentiate that, we're working out how quickly is that changing. So when I work out the second derivative, so I'm going to apply the derivative operator that I just talked about to the first derivative. So I'm going to do d by dx of dy by dx, which I can shorten to be d2y by dx squared. Hopefully it makes sense why this gets written the way I've written it there. d2y by dx squared. Okay, if I was writing that with this notation, I could just write f and 2 dashes. So what does this represent? Well, this represents the rate of change from here. So this is representing the rate of change of the rate of change. So basically, how quickly is the change changing? The most obvious example of that I can think of at the moment is in terms of mechanics. So for example, when you work out the speed of an object or the velocity of an object, you're working out how quickly its position changes in time. When you work out its acceleration, you're working out how quickly its speed changes in time. So you're working out the change of the position. So that's the second derivative, and that's what it represents. If I was to work out the third derivative, you won't need to do this, but if I were, I'd write that as d3y by dx cubed, or f with 3 dashes, and that would represent the rate of the change of the rate of the change of the rate of the change. And you can keep going with this, so you can work out, using differentiation, how quickly all the changes are happening. Right, let's have a look at an example of how we can, first of all, how we can differentiate twice. So here I'm asked to work out the value of d2y by dx squared when x is 2. So I'm going to first of all differentiate for the first time. So that's going to give me 12x squared plus 14x minus 8. So that's my first derivative. I am now going to differentiate for the second time to get the second derivative. And I want to know the value of this when x is 2. So let's substitute 2 into this. So that's 48 plus 14 is 62. Okay. So that's how you can find the second derivative. And we've talked about what it represents, but how can we actually use it? Well, what it can do is it can give us a shortcut for finding the nature of stationary points. Hopefully you've already watched the previous video where we talked about how we could find stationary points. So we differentiated to get the gradient function. We made it equal to 0, and we solved that to get the x-coordinate of those stationary points. In terms of working out the nature of them, we looked at, so if I know where I've got a stationary point at the value x equals whatever, if I want to know what type of stationary point it is, I know its gradient is 0 here. If I look just before that, so if I look at the x-coordinate that's just before this one and work out what its gradient is, so let's say that I've worked out the gradient is positive before my stationary point, and I've worked out that its gradient is negative after the stationary point. By doing that, I've been able to show that I've got a maximum. And we saw that if you have a negative gradient, a 0 gradient and a positive gradient, then that's a minimum. If we have a positive, a 0 and a positive, then that's a point of inflection. And finally we saw if you have negative, 0, negative, then that also is a point of inflection. That's quite a long way of doing it. Now there is a shortcut that you can use using the second derivative that will help you in either the first case of a maximum or the second case of a minimum. Unfortunately, it won't help you for the points of inflections, but it will help you for the first two cases. Let me talk to you about what that shortcut is. So, once you've found the second derivative, if the second derivative at your stationary point is negative, then that means you have a maximum. If your stationary point, if the second derivative is positive at your stationary point, then that means you have a minimum. Now the best way I can think of explaining why that is, let's think about what happens when you have a maximum. So I've got a maximum here at this point, and I know the gradient is 0 at that point. So my function is increasing, the gradient becomes 0, then it starts decreasing. Well, at that point when it's just about to start decreasing. So if I work out the change in the change, which is what the second derivative is, the change in the change, well, it kind of makes sense that it's going to be negative here because your function's about to start decreasing. So you would expect the change in the change to be negative because your function's about to start decreasing. And in a similar way, when you have a minimum here, well, my function is about to start increasing. It's about to start going up. So therefore I'd expect the change in the change to be positive because it's about to start going up. So let's just rewind for a minute there. So we find our stationary points. So we differentiate, we make it equal to 0, we solve it. once we know where the stationary points are, we then differentiate again to get the second derivative. We substitute our value of x in. If we get a negative, we know that stationary point is the maximum. If we get positive, we know our stationary point is a minimum. If we get 0, unfortunately, it doesn't tell us very much. It would be nice if we could say, okay, well that means it's a point of inflection, but we can't do that, unfortunately. It doesn't mean it's a point of inflection. It means it could be a point of inflection, but it could still be a maximum, or it could still be a minimum. So this is a bit of a pain, because when you get the second derivative as being 0, it means you need to go back and use the method I showed you in a previous video. So working out whether you have, what shape you have, looking at the gradients of the points either side of your stationary point. Okay, so let's have a look at an example, which is this one. So it says find the stationary points on the curve of the equation given, and we need to determine whether they are maximum, minimums, or point of inflections. So first of all, let's work out the where these stationary points are. So let's differentiate. So I've differentiated. Now let's work out where the gradient is 0, because that's our stationary points. Let's divide through by 6 to make this easier. Okay, so I've got a stationary point at 4 and at 1. Let's work out the coordinates of those points. So if I substitute 4 into my original equation to work out the y coordinate, so substituting 4 into here, I think I get minus 10. Substituting the 1 in up here, I think that's going to give 17. Okay, so we know where the stationary points are. I now want to work out, well, is this a maximum or is this a minimum? Or is it a point of inflection? So let's differentiate for the second time. So d2y by dx squared. What's my second derivative? So this was my first derivative, so let's differentiate that. And I get 12x minus 30. So when x equals 4, so if I substitute 4 into here, then I get that the second derivative, so 12 times 4 minus 30, well that's positive, that's 18, I think. So that's positive. Therefore, when x is 4, that's a minimum. Whenever the second derivative is positive, it means it's about to start increasing, so it's a minimum. Now let's check when x equals 1, what's the value of d2y by dx squared? Well, if I substitute 1 in here, that's going to be minus 18, which is negative. So the function's about to start decreasing, so therefore it's a maximum. So there we go. I found the two stationary points. This one is my minimum. This one is my maximum. And then we go. I've drawn that out. There we go. I've drawn that out so you can see. Yeah, it works. My coordinate 1, 17 is my maximum, and my coordinate 4 minus 10 is a minimum. So it works. Last example, I know it's quite a long video because stationary points is a big topic. It says find the greatest value excuse me, of 6x minus x squared and state the range of this function. So, greatest value, it's another word for what's the maximum value. So, if I differentiate, first of all, so let's work out let's differentiate this, it's going to give me 6 minus 2x equals 0. Let's find where this stationary point is. So x is going to be equal to 3. And so if I substitute that into my function to work out the y coordinate, or the value of this is going to be the maximum value of this. So if I work out, so 6 times 3 minus 3 squared, so 18 minus 9 is 9. So the greatest value of this is 9. So the range of the function is, I could say, well, f of x has got to be less than or equal to 9. If 9 is its biggest value. Just a very quick example to find the maximum point. You'll notice I didn't prove that this is the maximum rather than the minimum. I've just found the stationary point and assumed it was the maximum. I could prove it. I could work out the second derivative to differentiate in this again, but you'll notice I just get minus 2 because the x will disappear. So if I differentiate the second time, I get minus 2, which is negative, therefore it is a maximum. So I could do that. Or it's a quadratic and it's got a minus x squared, so I already know it's in this shape. So I already know it's just got the one maximum. Or there is actually another approach you could use for this that doesn't involve differentiation at all, and that's complete the square. But that's how we can do it using differentiation.